Hello and welcome to our latest installment of RTDology webinars produced by Burns Engineering, your temperature measurement experts. If you need temperature measurement supplies and/or expertise, think of Burns first. I'm Tony Miller, marketing contact for Burns Engineering, who will be helping to moderate today's discussion. Jeff Wigan, our sales and marketing manager, is also here today and may chime in from time to time. Bill Bergquist is our subject matter expert and will be leading the discussion today. Today's topic is RTDs versus thermocouples, which should last about 30 minutes, time for questions and answers. The Q&A portion of our presentation is oftentimes the most interesting part, so please post your questions in the chat section of the webinar dashboard, and we'll do our best to answer. This part of the webinar is dependent on your participation, so please ask lots of questions. For more RTDology topics, please check out RTDology.com or visit the RTDology page on our website under the Resources tab. Another great source for peer-led answers to your temperature measurement questions is the Temperature Measurement Group on LinkedIn. Finally, I'll turn you over to our resident expert, Bill Bergquist. Bill has an extensive background in temperature measurement and will be leading the discussion today.
Thanks for joining us, everybody. We're just going to go through and look at some of the factors on how to choose either an RTD or a thermocouple for a particular application. And I want to start off first with I'm going to go through some of the basic operations of thermocouples and RTDs, and then how to select the sensor for a particular application. But first, I want to just do a quick overview of the way I approach this question. And every application is just a little bit different. But I always like to start out with an RTD to see if it will fit in that application. We've made the decision to measure the temperature, and may as well do it the most accurate, best way possible. And that's typically with the platinum resistance thermometer. They're very accurate, stable. The measurements are fairly repeatable, and you can also pull it out of the system and calibrate it very easily. Temperature range -196 with liquid nitrogen up to 500 C is pretty much kind of a standard industrial type range. There are RTDs that will go over 500 C. Those are typically used in laboratory applications, though. So, and so if we look at this and just say, yep, we're going to use an RTD, and we'll try to find reasons to maybe exclude using it. Some of those are going to be durability. The thermocouple wins the durability contest every time. RTDs, some of them are made specifically for kind of heavy duty applications, but still the thermocouple is going to have the advantage there. And if we're going over 500 C, thermocouple is usually the best option. And if we need a super fast response time, we should have that. That's going to go to the thermocouple also, just because of the really small size. And when we look at some of how they're made, you'll kind of see that that technology can respond faster to temperature changes. So thermocouples, they're a real simple device. It's just two wires welded together to make a little junction. And that when you run this wire through a temperature gradient, or just, got the little junction in a hot place and the other end of the wires are in a cooler place, you can measure a voltage. And that voltage changes with temperature. So as the temperature goes up, the voltage goes up. So real simple device, and you can see that they can be, run kind of actually exposed to the process. Like if you're measuring air temperature, an exposed junction thermocouple can respond very quickly. They do have also the advantage of being able to be made in really small sizes. The wires we show here are probably like about maybe an 8 gauge wire, but you could go all the way down to, I've seen some of these, they use like 10 thousandths diameter wire to make them. The other big advantage is the temperature range. Here we show the different base types of thermocouples. There's type J, K, T, and E, and those are the most common types. They all have their applications, like the T and the E are rated for below 0. You'll also see some type Ks that that are used below zero. But in general, this is kind of the temperature ranges that they're capable of. The type K has the highest temperature range, and I think probably the type J and the K are probably the most two common types. Now we look at the accuracy of the thermocouple. Now this is where, the RTD has a huge advantage over the thermocouple. But if we look at the various types here, the type T is going to be the most accurate of the bunch. It has the most limited temperature range, though. The accuracy is available in just in general here. There's called standard limits of error and special limits of error. The standard limits, for the various types here, you can see that it ranges from, plus or minus a degree C up to about plus or minus 2.2 degrees C for the type J and the type Ks. And then the special limits are about half those numbers, so 0.5 to 1.1 degrees C. The reason for that difference is the kind of the purity of the materials that are used when those devices are manufactured. The higher the purity materials, the more accurate the sensor is going to be. It's going to be more stable over a long period of time, less drift. So if you're looking for, a thermocouple, heavy duty, that's fairly accurate, you want to make sure that you ask for special limits of error. There are some specialty thermocouples that are going to have accuracy limits greater than what we showed here, but those are pretty much application specific. Now, RTDs, on the other hand, these, it's just a resistor made with platinum wire. There's kind of two basic technologies here. There's the wire wound, which uses a little coil of platinum wire that's about, anywhere from 4 to typically 7/10,000ths diameter platinum wire. And as that platinum wire heats up, the resistance increases, and if it cools down, the resistance goes down. And it does this in a very predictable manner. The thin film version shown on the right-hand side here does the same. It's just a little film of platinum that's deposited on a ceramic piece. And these can be made very small size. Most of them are about maybe 1/8 inch square, maybe 20 thousandths thick. And their performance is governed by the two standards there, the international standard, which is IEC 60751, and the ASTM standard 1137. So yeah, that's, and these, of course, I guess you could say they even look a little more difficult to build, and that is true. They are more difficult to build. And of course, platinum is expensive, and so they do cost a little bit more, but you get that advantage of better accuracy, better long-term stability, certainly less drift than a thermocouple. Now, when the manufacturers make these devices, they have an interchangeability tolerance associated with it that is defined by those two standards. And these sensors are made, and the resistance is adjusted as close to 100 ohms at 0 degrees C as they can get. And we try to meet these tolerance bands on here. And you can see, if you look at the green lines, that's the IEC, what they call Class B. And then there's a Class A, which is about, twice the tighter tolerance band. And the ASTM standard has just a slight advantage in smaller interchangeability numbers than the IEC. And that's why this graph looks like it does. So we try and trim these sensors as close to 100 ohms as we can get right at 0 degrees C. But as you go away from 0 degrees C, either negative or on the plus side, that tolerance band expands. And there are equations and tables that you can look at to see what these numbers are. So if you are looking at like this IEC Class A sensor, for example, you can take any temperature in degrees C, that's what the little t here is, multiply it by 0.002, add 0.15, and that'll give you that interchangeability tolerance at that temperature.
Hey, Bill, we have a quick question here. What are the metals generally used in the wires for the thermocouples?
Oh, and thermocouples, there's quite a variety. Like this is going to be like a type J. One of the conductors is iron, and the type T, there's one of them is copper. Type K, the international, I think it's International Nickel Company, has a couple of trade names like Chromel and Alumel, which I don't know the exact chemical analysis of either one of those, but they do use different metals, and they'll all behave differently. They have some are better at higher temperature measurements, and some can be a little more accurate, like the type T. There's also like the type R, S, and B as in Bravo thermocouples. Those are made with one platinum conductor, and then the other is a platinum rhodium alloy. And those are capable of very high temperatures. They'll go up to, I think it's roughly 2000 degrees C. There's also a thermocouple, which is a type, I don't know, sometimes I see it called a type C, and others it's a type W, but it uses, one conductor is tungsten, and that has to be, if you can imagine, like it can do really high temperatures, but it has to be inside of a kind of an evacuated packaging system. And if you think of a light bulb, like the old incandescent light bulbs that had the little tungsten coil to illuminate when you run the current through it, it just starts to glow. That light bulb is, it's in a vacuum in there. As soon as it sees any kind of air, it just oxidizes and breaks and burns out right away. So those are just some of the metals. People have experimented with practically anything you can think of to put together a thermocouple.
We do have a follow-up question here, Bill. It says the metals are different for each wire, correct?
Yeah, they have to be dissimilar metals.
Yep. And then we have a new question. For tolerance nomenclature, how do you know that at grade B or which is the best?
Well, I get this question a lot because both of when the sensors are made, like with a wire wound sensor, all that we're doing is trimming that coil of platinum wire to get as close as we can to 100 ohms. And if you look at kind of standard manufacturing practices, you're going to have a little bit of end up with kind of a bell curve where some are going to be, really close to 100 and others are going to be kind of on the outskirts of that. It doesn't mean that the sensor is any more or less stable, repeatable than another one. It's just that when that tolerance was trimmed, it got a little bit closer to 100 ohms than the one that's, on the kind of on the outskirts of the tolerance band. And so when you, now if we were to take one of those sensors and calibrate it, well, if we were to take like a grade A and a grade B and we put them through a calibration, and so this calibration characterizes the exact resistance versus temperature relationship. And if we do that and you end up with some temperature coefficients, and you can take all that information and you can mathematically calculate the resistance at a given temperature or vice versa. And both are going to have the same kind of uncertainty of those measurements. So it's not that grade A is any better than a grade B. It's just, it was adjusted a little bit tighter at 0 degrees C when it was made. Hope that answers that question. It gets to be a little bit complicated, but the actual performance of either one of those sensors after it's been calibrated is dependent on the accuracy of the lab that did that calibration. For example, our uncertainty of the calibration, uncertainty of the measurements that we make for that calibration, either one of those is plus or minus 0.0253 C, which you run through any of these little equations here, it's way tighter than what you end up with by just using kind of sensor right out of the box with that interchangeability tolerance. I do have a lot more information on that on several other presentations. And I think there's a link at the end here. Tony, is that on the YouTube channel? Okay.
Yep, should be.
Okay. So
There's been a lot of people asking if these slides can be available afterwards, and what we do is we put it together in a video that you can stream from YouTube. Should be available in a couple of days. And then we also have another question. I want to know why the RTD have interchangeability, maybe oxidation.
No, it's just when it was made, it gets trimmed to that 100 ohm number at 0 degrees C. It has nothing to do with anything else. The sensors are all made identical. It's it's just that's all it is. It's just trimmed tighter at 0 degrees C.
Say, Bill, this is Jeff. So I think one of the ways that's easiest that I've explained it to people is interchangeability. When a manufacturer, when we make the sensor, some of these are going to fall on the 100.0 something or 100.1 ohms, and some are going to fall at 99.9 ohms. Essentially, it's the tolerance that the manufacturer has to make the sensor and claim that it fits either within the Class A tolerance band or the Class B tolerance band. So if you say you buy 10 sensors from us, 5 may be on the 100.1 ohms and 5 may be at 99.5 ohms or something like that. So it's really that tolerance. That's all it is starting a little tighter. So Class A is a little tighter than Class B is. So depending upon what you're trying to do in terms of accuracy, what kind of accuracy you're looking for, you may want to start with a Class A if you're looking for a tighter accuracy, which just gives you a little bit more room for your other air sources that come in when you're taking a measurement. That's really what it is.
All right. Is that it, Tony? We should move on then?
Yeah, you can move on now.
All right. Temperature range. The wire wound sensors typically have a wider temperature range than the thin films, although I have seen thin films rated up to about 850 C, I think it was. I'm sure they had to be packaged correctly to be able to do that and do it repeatedly and maintain their stability. But in general, you'll find that they're kind of limited to wire wound is this minus 196 to 500 C, and the thin films about minus 50 to 200. The other part of that, a lot of times thin films are made to be more durable, and the materials that you use to do that have the lower temperature limits. Like there might be some silicone rubber or some heat transfer type component that it's a lot of organic type materials that just have that 200 C or 400 F upper temperature capability. So that's kind of why you'll see this as being very common among manufacturers. They'll have kind of basically two RTD temperature range groups of parts. Externally, they all look the same, but inside they're a little bit different. If we do a little comparison here between the wire wound and the thin film, wire wound resistance, most of them are made to 100 ohms at 0. There are some 200 and 500, but after you get, those are all pretty specific applications. If you can imagine doing 1,000 ohm wire wound, it takes a lot more wire. It's really expensive. And at that point, the thin film is a much better way to do it if you need a 1,000 ohm sensor. Accuracy, again, the wire wound is about twice as accurate as the thin film. Most of the thin films are only offered in like a Class B interchangeability band. You will find some that will be Class A. One other thing I did not mention about interchangeability, the standards have been updating, and I think there's a Class AA now as well as a Class C. Let's see, repeatability within their temperature ranges, they're about the same. Time response, wire wound actually has the advantage over the thin film only because of the packaging that's typically done with thin film. You can take a thin film and put it in a little copper tip on the sensor and get really fast response time out of it, down to about maybe 2 seconds. Actually, I should probably clarify here. I shouldn't really say time response. It's the time constant, which is the amount of time it takes the sensor to reach 63.2% of a full change in temperature. So if you're going from 0 to 100 degrees C and you had a time constant of 2 seconds, after 2 seconds, you would be reading 63.2 degrees. So kind of a rough guesstimate of what happens there. And to get the full temperature change, or nearly so, if you take that number times about 4, so it'd be about 8 seconds to reach the full temperature change. There's some good explanations about time constant on Wikipedia. Steps through and kind of shows all the calculation. But at any rate, wire wounds typically just your standard industrial offering. Going to be just a little bit faster than the thin films. Vibration, thin films do have the advantage there if they're packaged correctly, and that's a big if. Stability, and this is kind of long-term drift or stability, whichever you want to call it. The wire wound does have the advantage, and of course there are caveats there too. If there's more vibration or temperature cycling and some other things, the thin film, because of its durability, may end up being way better than the wire wound. So, but just in general, wire wound is going to be more stable. So when we look at just kind of comparing, I put together some tables here that looks at some of these factors for choosing the sensor. And hopefully this may help some of you go through and decide which one is going to be the best for what you're trying to accomplish. First thing we talked about accuracy. We didn't really talk about calibration too much, though. Thermocouples, because of the way they work, you really need to just do a comparison calibration right in situ, right where it's located with all of its lead wires and instrumentation hooked up to it. Take a temperature standard, and like if the sensor's in a thermal well, if you could pull that sensor out, put your standard in there, measure and see what it does. And that's kind of the way you'd have to calibrate it. You can't really pull it out, take it back to the lab and check it, because it's going to be different than what it is installed in the process. RTDs, on the other hand, you can pull them out, take them back to a lab, or you have portable calibration equipment. You can just pull it out, check it. Very simple to do. You can also improve the accuracy by taking the calibration information. So if you have the probe calibrated, get those calibration coefficients and the temperature coefficient for that specific RTD, you can get a lot better accuracy out of that by matching it to a transmitter or whatever device you have it connected to. Stability, again, RTD's got the advantage there. Repeatability. With a thermocouple, it varies a lot, usually based on temperature, the atmosphere that it's in. If you've got a reducing atmosphere or oxidizing, you're running at a really high temperature, thermocouples can drift quite quickly. RTDs are more stable within their temperature range. Even if a thermocouple is used in that minus 200 to 500, the RTD is still going to be more stable. Temperature range, again, thermocouples got the prize there. 1180 C, that's 2100 Fahrenheit roughly. Response time, yeah, if you use a bare wire sensor, they can be really fast, a millisecond or two. RTDs, about the fastest I've put together kind of in typical industrial packaging is about 2.5 seconds. Some are a little bit faster, maybe down to 1.5, but 2.5 is kind of a good solid number that you can trust. And then size, there are some RTDs that are very small. They tend to be very delicate. Most of the industrial stuff you'll see, 1/8 inch is about the smallest. There are some that will be, maybe 80 thousandths. If you get down any much smaller than that, you end up with some durability issues. And with thermocouples, of course, you just have the two wires hooked together, and they can be really tiny wires. I think I mentioned maybe 10 thousandths diameter. I think I've seen, I think Omega had a photo one time of a thermocouple glued to the back of a bumblebee or something. So it can be really small. You certainly couldn't do that with an RTD unless you just were using exposed platinum wire, but it still would be maybe a little too heavy for the bee to still be able to fly. So at any rate, that's kind of just a few of the things to look at. When we get into some of the environmental issues here, this can be, we're looking at the vibration, ambient conditions, and the control system you have it hooked to, and then the distance between the sensor and the control system. That can be a huge factor. Vibration, thermocouples, if you have high vibration, or if you used an RTD and it tended to drift quickly out of tolerance, or if it went open circuit quickly, you'd certainly want to switch back and use a thermocouple in that application. Ambient conditions, usually that's not too much of a factor here. The one that I can think of, if the ambient conditions are real high, some of the RTDs have a little transition piece where the external lead wires are potted in epoxy, and a lot of those epoxies have since they're organic materials, they're going to be limited to about 200 C or 400 Fahrenheit. So that'd be about the only limitation for ambient conditions. And most control systems, it's just a setting to go from thermocouple or RTD. But the distance between the measurement point and the control system, or it might be a chart recorder, whatever it is, thermocouples are real sensitive to electromagnetic and radio frequency interference. And so you really need to use shielded thermocouple extension wire to avoid that. The RTDs are less susceptible. And just kind of as a rule of thumb, if you're going over, 250, 300 feet, it's probably a good idea to put a transmitter mounted right at the RTD. And then you're running just a current, typically a 4 to 20 milliamp current signal, which is a lot more robust than trying to measure RTD resistance over a 300-foot long cable. And if you're using a 3-wire circuit with the RTD, there can be some significant lead wire errors going much over 20 or 30 feet. So either switch it to a 4-wire system or put a transmitter mounted right at the RTD location, or as close as you can. The other thing with thermocouples is the cost. Sometimes the thermocouple extension wire can be a little spendy, and you're probably better off spending that money on a transmitter mounted right with the thermocouple at the process location. Here I mentioned the RFI and EMI considerations, energy costs. This is where I get back to always start with an RTD. Because if you're heating or cooling a process, you're going to have much better control over that and much better control over the money that it takes to heat or cool that process if you have an RTD that's been installed correctly and gives you a good, accurate, repeatable, long-term measurement. Initial cost of these, thermocouples, as you can imagine, are dirt cheap. They're, $10 to $80 roughly for most of them. RTDs are, if you look at the good ones, they're going to be at least 100, some up to, at least probably a couple hundred, right in that range. That's just for the temperature probe. And some of that, if you were thinking, well, let's just use cheap little thermocouple in there. But, if it drifts fast and it goes out of tolerance right away and you're using up extra energy that you don't have to, kind of spending the money ahead and with an RTD can give you the lowest life cycle cost. So that's kind of a money consideration out of this whole thing too. Some typical applications here. You can imagine pharmaceuticals. They usually very tightly controlled. They've got the third-party watchdogs looking over their shoulder. So they want something that's, very accurate, very repeatable, very stable, something they can calibrate easily. Same goes for kind of the chemical and tire rubber industries. Some of the like the tire presses where they're curing the rubber for the tires, it has to be controlled very accurately, so you end up with a good quality tire. Fuel custody transfer is another where like you're taking gasoline out of a might be an underground storage tank, putting it into a delivery truck on a 100-degree day. Of course, that fuel expands when it warms up. And you need to know the temperature of that fuel as it's going into the truck so that you don't overfill it and have an overflow situation. So that sensor has to respond very quickly and it has to be very accurate. So they can use that temperature in the volume calculation. So if the truck holds 10,000 gallons, at 60 degrees in the underground tank, but it's 100 degrees where they're delivering, it's going to expand quite a bit. Thermocouples, there's your heavy duty applications, exhaust gas. You can imagine high temperature, a lot of vibration. Some bearings, refinery applications, areas where there's high temperature, high vibration. And another little quick guide here, you can just kind of step through some of the situations here and just a recommendation. So again, RTD, start that way. If there's some factor in your process that's going to exclude it, then we'll go look at a thermocouple. And I think with that, we can jump off to more questions.
Yep. We got a couple here.
All right.
One is the complication with calibrating a thermocouple limited solely to the length of lead wires used, or are there other environmental factors?
Well, the actual, like how far it's immersed in the process can be a factor. The length of the lead wires, the quality of the connections, and if that wire is running by any, if it's being affected by any RFI, EMI stuff, if it's a steady, it's typically just the length of the wire and the connections, and then how the part is actually installed into the process. Those are the factors that you can't simulate back in a laboratory, which is why you just need to do the in situ calibration.
Okay, and then we also have, are the response time numbers you're providing on the slide 63% response time values?
Well, it's the time constant, and so it's going to be the numbers that we showed there, 4 seconds for the wire wound and 6 for the thin film. That is the time constant. So the way we do that test and the way the standards kind of define it is the probe is put into, we typically take the probe, stick it in an ice bath and cool it down to 0 degrees C. And then we'll put it in water moving at 3 feet per second. That's at room temperature. And the time it takes for that probe to respond to 63.2% of that step change in temperature is the time constant. So it'll take that wire wound sensor from ice to room temperature 4 seconds to get up to 63.2% of that temperature change. And it's a, and if you look at 2 time constants, it raises that by half of that amount again. So it's about, it's getting close to 90% then. I don't know the exact numbers off the top of my head, but by the time you get to about 4 time constants, you're almost to 100% of the step change in temperature. So it's like, you can't look at that sensor and say, okay, it's got a time constant of 4 seconds and I'm going to stick it in here and wait 4 seconds and I got my temperature. That's not it at all. You're going to have to wait 16 seconds for it to really kind of stabilize.
So this is Jeff again. One of the ways to understand time constant versus time response is time constant is what all manufacturers, that's the way all response times are spec'd out or reported on any kind of sensor. Time response, on the other hand, is what's actually happening, how long it takes in your particular process. And so the diameter of the sensor, whether or not it's in a thermal well, what the material is, all of those things factor into what the actual time response is. So at best, the time constant from manufacturers just gives you a comparison point between different sensors. Well, this one reacts a little faster than this one. It doesn't actually tell you how long it's going to take to respond in your process. So that's something that's very specific to the process it's going into.
Yeah, that's a good point, because we'll use water, but of course other materials are going to respond differently. Even at the same flow velocity, they could be wildly different. I have noticed that, especially in the kind of the food beverage industry, where you have the process material that has a really high fat content, you can put the probe in there. It's going to have a much slower response time than in just water. And I think sometimes those terms are kind of used incorrectly. You'll see time response, time constant, but to be really correct, what we publish anyway is the time constant, and we typically have a kind of little explanation along with it with some of the various different parts.
And just one more thing to add to that is sometimes there's a misconception that the fastest time constant is somehow a better sensor, or it gives you a better measurement because it's quote unquote faster. In reality, the sensor only needs to respond as fast as the process is changing. So if it takes if it takes the process 30 minutes to stabilize, the fact that you have a sensor that responds in 3 seconds, 5 seconds, or even a minute doesn't really matter, because it takes 30 minutes for the process to change. And in fact, we've run into several situations with applications where the sensor is changing too quickly, and the control system is continually trying to chase that temperature, and that causes problems as well. And so then we're trying to dampen the response of the sensor so that it doesn't change so quickly. So you have to be careful about, just because it has a very quick time constant, that doesn't mean that it's necessarily a better sensor, that you should go with it. You really need to match up how quickly your process is changing with the sensor to make sure you get the very best measurement.
Well, if you have any other questions, feel free to throw those in now. We'd like to show our RTDology page. You can just go to YouTube and just do a search for RTDology. I could probably throw Burns Engineering in there also and probably get to the same place. But we've got several presentations there on accuracy and pretty much everything there is to do with measuring temperature with RTDs and thermocouples. And then we're always looking for new topics. So if you have something specific, you can just send it to info@burnsengineering.com, and we can put something together for the next session that we do. All right. Well, Tony, is that going to be it for questions then?
Yeah, it looks like that's it for questions. If anything else come up. So.
Okay. Well, thanks everybody for joining us today. And, sure, let us know if you have any other questions, comments, and get a hold of us later. Send questions to just info@Burns Engineering also.
Thanks, everyone. We'll see you.